Okay, ladies and gentlemen, this afternoon I'm going to change the direction slightly. Up until now we've mostly been hearing criticism of what the IPCC's got wrong, which is many things, if not everything. And there'll be a little bit of that in this talk, but I'm not going to allow them to use up all my time and my bandwidth. I want to tell you something about a better, new and better theory of climate. And it's quite a wide-ranging story. It's going to involve a tour of the entire solar system. And I've got to squeeze all this into 30 minutes or so that I can leave plenty of room for questions at the end. So, without too much more ado, I'm going to take Bob Carter on what he said this morning about widening the context. And this is something that we need to do in order to really understand what causes changes in the Earth's climate, on what timescales, and how it all operates. So, first of all, the big mistake from the IPCC, which is that they tell us that according to the best science they've got, that CO2 causes about 20 times more climate change than solar variation. Now, here they've got solar variation, you know, about 0.1 watts per metre variation. You'll notice that the albedo change of cloud due to land use comes in here. There's nothing really much about clouds anywhere, and even if there was, it would come under anthropogenic rather than anything to do with natural causes like the sun. This is completely wrong, but I'm not going to waste too much time, but just think about the reasons why they want to say that the sun has hardly any effect. Now, the first reason that most people come up with is, well, of course, they want to tax us all for emitting CO2, so they've got to say that the sun doesn't do anything. But actually, there's another reason, and that reason is that because they can't predict what the sun's going to do in the future, they can't have a model that tells you what the climate's going to be in 2100 if they admitted that the sun was a major factor in climate. And so this is another strong reason why they want to convince us that the sun has nothing to do with it, because if they can't make a model that makes a prediction 100 years out, what are we paying them for? Why would they exist? Now, the thing is that until now, mainstream science hasn't been able to work out what causes solar variation, and neither could the ancient peoples of the world. They did understand that the sun was a very important factor in their lives, which is why they had gods dedicated to the sun. So, you know, we've got the Hellenistic god Helios in his chariot drawn by the four-winged horses around the heavens. Back in Egyptian times, Ra, the big orange disk of the sun. And in Mexico, in the Aztec culture, the sun was also extremely important. In fact, when crops failed, they would sacrifice people and pull their hearts out and wave them at the sun to propitiate the sun god and get him to help them out. So, and even I particularly singled out this lovely image as an ancient Syrian sun god, Yahweh, who was regarded as the deity of light, truth and honour, which I think is a great motif for my intention in the climate debate, which is to bring in a bit of honesty and truth.
American spelling on that, is it?
And I think it's a lovely image. I love the curly hair, you know, sort of, it's very like the surface of the sun with a big whirling convection currents and so on. Fantastic. And I think if you count up these rays, there's probably 22, which would probably please peers as well. So,
can you go back there?
150 AD, Claudius Ptolemy, known for his superb mathematical work in being able to predict where planets were going to be in the heavens, but he also wrote another major work which isn't so well known, as well as the Almagest. He wrote a book called the Tetrabiblos, which was a more theoretical, more speculative work in some ways. A lot of people regard it as being sort of quite foundational to the study of astrology, but he discussed the nature of the bodies in the heavens and how they related to the Earth, and so he's one of the pioneers really of the solar-planetary theory, which I'm going to outline. And although in a lot of senses you could say it was theoretical and even speculative, he had some insight, and obviously we should respect him for his great mathematical prowess, and made me think that his insights are worth looking at and thinking about. And he said that the active power of the sun's essential nature is to be found in heating and to a certain degree drying, and that this observation is based on the configurations of the sun and moon successively. So he would talk about the way that the moon would moisten things at night, and you'd have a dew on the ground in the morning, and then the sun would come along and dry that dew out. But he also observed the motion of the moon passing through the stations of the ecliptic, and also the sun, obviously the 4 stations of the year being the equinoxes and the solstices. So he was formalising these relationships and speculating on how it might relate to the motion of the planets and their positions in the sky. And interestingly, there was some confirmation of this idea that the positions of the planets were important when they're at certain angles, such as 60 degrees, 120 degrees. In 2007, a NASA scientist called Ching-Che Hung, who was studying the occurrence of solar flares, found that when certain planets like Mercury, Venus were overhead, you might get a flare. You might get one when it was 30 degrees off or 60 degrees off. And that those were, and he made some predictions on the basis of these observations and got them right. So Ptolemy's insight was worth something. Moving on a few hundred years, Johannes Kepler, at the end of his book Harmonies Mundi, The Harmony of the World, he allowed himself a chapter of some speculative ideas, and in that he mentions that the harmony of the world, and by the world he meant the whole solar system, that the harmony of the world comes from the 6 planets evolving and making consonances to the sun, which is at the centre of all the circuits, all the orbits. Immovable but rotating unto itself, so he knew about the rotation of the sun. He wasn't quite right about the immovability, and we'll come back to that very soon. But he understood that the geometry in the heavens was important, and he found various ways of expressing the relative distances of the planets from the sun, which related to geometrical ideas. So this idea was that the orbit of Saturn, the outermost planet known at the time, that if you put a cube inside that, touching it, and then another sphere touching the faces of the cube, the centre of the faces of the cube, you'd get the orbit of Mars. And then with a tetrahedron inside that and another sphere inside that, you'd get the orbit of the Earth, and so on in towards the centre of the sun. And these geometric ideas, he noticed that the golden section, phi, was all over the geometry that he found, and he speculated about that too. But the other thing that he had a good intuition about was that not only does the light go out from the sun, but these returns of every lovely harmony are collected in the sun. The forms of movements by twos flow together and abound into one harmony. And I think what he's driving at there, the movements by twos, what he's getting at is that there's a two-way relationship between the motion of the planets and the way the sun acts on the planets, and that there's a kind of a feedback there, and that all true systems, like the sun, if we're going to call it a solar system, all true systems contain cybernetic feedback. So one thing is affected by another, and those effects bounce back to the first thing. So you can't ultimately separate cause from effect in a simple linear way here. You have to think about the thing as a whole. Moving on to Newton, who didn't do so much speculative stuff, he famously said, "I frame no hypotheses."
He just told you the truth.
Although he did come up with quite a few speculative things, in fact, but what he did do was he estimated the relative masses of the known gas giant planets and the Earth and the Sun, and he realised that actually the Sun isn't immovable at the centre of the system. Not only is it spinning, but when the big gas giant planets like Jupiter and Saturn come together on one side of the Sun has to sort of lean back a bit like a hammer thrower at the Olympics. If he had 2 hammers, one Jupiter, one Saturn, and he's swinging them around, if they're opposite each other, he stays more or less upright. But if they're both on one side, he has to lean back to counteract the mass. And so the Sun actually does a complex dance around the centre of mass of the solar system. And what we found is that this actually then has an effect on the rotation of the sun and the rotation of the plasma layers around the sun. And this affects sunspot production and so solar variability. But it wasn't until 1965 that we got the computational power. And when Paul D. Jose, who was working at Los Alamos Observatory, decided to actually get numerical about this. He had the computing power to do it, and he worked out exactly what the motion of the sun was relative to the centre of mass of the system over the years, and this runs from 1945 to about 1996, I think. Interestingly, another person who investigated all this was a guy called Theodore Landscheid, and he worked out that when the path of the sun, when the path of the centre of mass of the system just skims the surface of the sun for several years, you always get a slowdown in solar activity. It's quite sudden and quite powerful slowdown. And indeed, we find here that between about 1969 and 1973, this was an occasion when it was just skimming the surface of the sun, and indeed we did get a very low solar cycle during the 1970s, an anomalously low one compared to the higher ones either side. So his conclusion was that the dynamic forces exerted on the sun by the motions of the planets are the cause of sunspot activity. I wouldn't put it necessarily as strongly as that, and I'm not going to enter a debate at this point about it. But one of the things he did spot was that at a period of around 179 years, the big four gas giants come back into a relatively similar configuration around that period. Sometimes it drops back to about 160, but it averages out about 179. And also that 179-year period roughly coincides with the gap between the Maunder minimum and the Dalton minimum, and the Dalton minimum and where we are today, which is going into another one of these grand minima. So that was then taken up by Ivanka Charbatova in the late 80s, and she looked into this in more depth and more carefully, and this series of graphs runs right through from the 1200s through to the start of the 1900s, this way. And what she found was that for 60 out of those 180 years, the sun would move in quite a harmonious way, drawing this sort of three-leaf clover shape as it went round the centre of mass of the system. And then for the next 120 years, it would go into a kind of a chaotic mode. And this is largely due to the configuration of the outermost two gas giants, Neptune and Uranus, having an effect. When it's mainly just Jupiter and Saturn, you get this kind of trochoidal, triple swizzle motion, quite harmonious and regular. So it's a bit like when you're stirring your tea. If you're stirring it regularly, everything starts whizzing around quite fast. If you then suddenly move your spoon around in a random way, everything comes to a stop and it slows down a lot. Well, there's something similar going on with the way that the plasma rotates around the surface of the sun and causes sunspot production. So she said that this gives us a precise and homogeneous basis on which it became possible to study the solar terrestrial and climatic variability. Now, we'll just nip back in time a little bit to the start of the 1800s. So William Herschel, who discovered Uranus, he said he noticed that from 1795 to 1800 there were almost no sunspots visible. And then they came back. But he said that sunspots with big shallows, ridges, nodules and corrugations instead of small indentations, which is what we saw at the start of the latest solar cycle. There were only little tiny specks that weren't really good enough to be called sunspots at all. May lead us to expect a copious emission of heat and therefore mild seasons. And to try and verify that, he struck on the idea of having a look at the way that the price of wheat varies, because his reasoning was warm years, plenty of wheat, lower price. And he struggled really to get the information, but in 2003, two doctors, Pustelnik and Yongdin, did a careful study of this and found that indeed it was absolutely the case that the length of the solar cycle related to the periods between bursts in price, going back hundreds of years. So Herschel was vindicated. Now I want to go back and start to talk more about what I'm talking about with the rhythm of the solar system. And this was another insight from Johannes Kepler, who'd found all these phi relationships, the golden section basically, which is the ratio between a line which is 1 unit long and a line which is 1.618 units long. It's actually a noble number with an infinite number after the decimal point. But he commented that the theorem of Pythagoras and the golden section, the division of a line into mean and extreme ratio, the first we may compare to a mass of gold, the second we may call a precious jewel. It's a very flowery language, but he felt that these were really important mathematical concepts which help to explain the underlying cohesiveness of the motion of planets in the solar system. And in fact, that's been borne out by my own investigations. If you look at this diagram, again here we have a golden section rectangle. And so if this is 1, then this is 5, roughly 1.618. And if you take the Kepler triangle here, and you fit into it the biggest possible squares you can, sequentially, then you'll get 1 of that size, 1 of that size, and then you can fit in 2 of that size, and then 3 of that size, and then 5 of that size, and 8 of the next size, and 13 of the size after that. And this is the Fibonacci series, 1, 1, 2, 3, 5, 8, 13. And the Fibonacci series is very closely related to the golden section. In fact, as the numbers head towards infinity, as Christopher knows, as the numbers get bigger and bigger, the ratio between the numbers gets closer and closer to the exact golden ratio. But what this shows is that as well as converging to the golden ratio, which incidentally the Fibonacci series does faster than any other similar number series, and that's important for consideration maybe of conservation of energy in the solar system. You can also generate the Fibonacci series starting from the golden section through a process of quantization, fractal quantization, which is what we're seeing here. So although this is an abstract concept, it could actually be important to our understanding of why it is that many of the orbits in the solar system relate to each other by adjacent pairs of Fibonacci numbers, or a relationship which involves a power of phi, like phi squared or phi cubed. So at the end of 2013, myself, Nicholas Lorna as head editor, a great astronomer, Jana Solheim, and a dozen or so other contributors, or 2 dozen or so other contributors, we put together a special edition of Pattern Recognition in Physics, in which we laid out our ideas about the relationship between motion of planets in the solar system, solar variability, how that affects the Earth, and it upset some of the IPCC authors who wrote a stiff letter to Martin Rasmussen of Copernicus Publishing. Their strapline is publishers of the innovative science publishers. I call them the innovative science unpublishers, because what Martin Rasmussen did was he rolled over at these complaints from the IPCC and he shut the journal down. He just closed it. So instead of getting debate and discussion about our new theory, they just shut us down and tried to brush us under the carpet. The effect of that was, instead of a few dozen interested people downloading our papers, 10,000 people have downloaded our papers. So, and in my main paper in that publication, I said that in fact the stability of our solar system over long periods of time is contingent upon certain frequency ratios lying very close to noble numbers, and the most important of those being phi, the golden section, because very, very many orbitally resonant ratio pairs of planets are in a relation of 2 to 3, or 5 to 8, or 8 to 13. 2 to 3 is a particularly strong one. 1 to 2 is so strong that they think that was responsible for kicking gas giants out of orbits that they were in near the start of the solar system and them ending up somewhere else completely. So these are powerful forces at work, and astrophysics knows that these are big and powerful forces. When you get exact ratios like 2 to 3 between orbital periods, you get big powerful transfers of energy occurring. So what we see now in our stable solar system is that often the ratios won't be exact, they'll be close. And that's because if they become too close to exact, lots of energy gets transferred and the smaller of the two planets gets pushed away into a slightly different orbit. And that then takes it away from the ratio. But it seems to want to gravitate back towards the ratio. So it ends up at a sort of fairly happy medium. It's dynamic, things change as other planets come nearby and kick a bit of energy here and there. And the whole system shuffles along, occasionally dropping a beat here and there to keep everything more or less in line. So one of the major discoveries I made a few years ago, 2011, was that if you not just look at the planets in sort of the XY plane as they go around the sun, but all of their planes of orbit are tilted relative to one another. And the sun itself is tilted off at 7 degrees from the average plane of all the planets. And so what you find is that the big gas giants spend years at a time either above or below the solar equatorial plane. And if you average that over if you average where the centre of mass is of the entire system over 2 Jupiter orbit periods, so that Saturn's information isn't messing things up too much, you generate this green curve. And so this is the kind of, if you like, the z-axis motion of the sun relative to the centre of mass of the system. And this graph's running from 1840 to 2000. Now, that's the green curve. Now, on this plot, the blue changes in Earth's length of day. And what this implies is that the big gas giants moving above and below the plane that the Earth's orbiting in affect the Earth's rate of spin. Now, we're only talking 2 or 3 milliseconds over a couple of decades here. But when you actually calculate that if the solid Earth is slowed down by a couple of milliseconds, the oceans, which aren't fixed to anything, want to carry on travelling at the same speed they were before. Yes. So they pile up against Africa or they pile up against South America, depending whether the Earth's speeding up or slowing down. And this causes the upwelling of large amounts of cold water and nutrients that fish like from the deeps. And then that cold water then flattens out and spreads out across the surface of the ocean over the course of sort of 15 years or so. And this contributes to the ups and downs of the Earth's climate. By the way, and incidentally, it's worth noting that solar activity was high at the end of the 1800s. It dropped to a low around 1900. It got quite strong in the middle of the century, and then we had that quick dip in the 1970s that I mentioned, and then it got strong again up to 2000. So this curve also relates to solar activity as well as changes in the Earth's rotation rate. And also, if you look at global temperature, if you detrend the global temperature series a bit, and I'll explain why we have to do that, that also dropped from the 1880s to the start of the 1900s, then got warm around the middle of the century, around the 1940s, and then got cold in the 70s, and then warmed up towards the end of the century. So we have a rough correlation here with solar activity, global surface temperature, rotation rate of the Earth, and the motion of the gas giant planets. So this is the beginnings, this is the bare bones, this is the kind of the long scale stuff of the new theory of climate. This is saying that because we're part of a whacking big solar system, we're lifting our eyes up a little bit further than just looking at the Earth's atmosphere and chemical changes in it and saying, well, what lies behind those? You know, and the answer is solar variability, the motion of the gas giants affecting Earth's rate of rotation, and these, you know, and that at longer time scales, the effect of the gas giant's motion is to change the shapes of Earth's orbit over 100,000 years or so, which gives us the Milankovitch cycles, the angle that the Earth tilts, which varies, as Piers said the other day, over a cycle of around 41,000 years, and the precession of the equinox, which, as Piers said, is around 26,000 years. And all these periods can be related to interactional numbers of orbits between these gas giant planets.
What's the name? Gas giant? Sure.
The gas giants are like the big planets like Jupiter and Saturn, Uranus and Neptune. Yes, they're primarily made of gas. So one of the most clear-cut cases in the solar system of of orbits pushing each other around and coming into a synchronization is the moons of Jupiter. Now, as Piers mentioned yesterday, they're tiny in comparison to the size of Jupiter. But Jupiter's a pretty constant shape, and these moons are more or less rotating, revolving orbitally around Jupiter's
they're
equator.
not facing, aren't they?
Equator. They always keep the same face facing towards Jupiter. Yeah. What we're interested in here is the relations between the three. Now, it was thought for a very long time, and you'll see this in any textbook that you look it up in, that Ganymede is in a 4-to-1 ratio with Io, and Europa's in a 2-to-1 relationship. And this is talking about the orbital periods. But it's not quite true. It's actually 4.04-to-1. You actually get a more exact set of ratios if instead of just looking at the orbital periods, you look at how often they come into conjunction, like those two just passed conjunction. And this one's about to come into conjunction with this one. There. And what we found was that rather than a 4-to-2-to-1 relationship, if you actually look at the conjunctions instead of just the orbital periods, you get a much more exact 3-to-2-to-1 ratio. And of course, 1, 2, and 3 are the numbers in the Fibonacci series again. So this is a very clear-cut case because Jupiter's so massive and these moons are so small. Elsewhere in the solar system, where you have big planets that are quite a long way from the body that they're revolving around, they affect each other more, so it becomes a more complex relationship. So, for instance, if you look at, we can run the Fibonacci series through the entire solar system very simply. I'll just do it verbally because I don't want to bore you with too many numbers on screen. But if you think about the outermost ones, then in a period of around 170 odd years, then you get one orbit of Neptune, you get one Uranus-Neptune conjunction, and you get 2 orbits of Uranus. If you then come 3 times closer to the Sun and divide that time period by about 3 as well, you get a 60-year period where you get 2 orbits of Saturn, 3 conjunctions between Saturn and Jupiter, and 5 orbits of Jupiter. And then if you come another 8 times closer, or 21 times closer than your original group, you get into the small planets near the Sun. And what do you find? You find that there are 5 conjunctions in an 8-year period, so you come 8 times closer and divide the period by around 8 as well. And you get, in an 8-year period, you get 5 conjunctions between Earth and Venus, 8 orbits of the Earth, 13 orbits of Venus, 21 conjunctions between Venus and Mercury, and 34 orbits of Mercury around the Sun. So, in a very simple way, I've described all the planets in the solar system, the main planets, and you get 1, 1, 2, 3, 5, 8, 13, 21, 34. And the error on that is only a percent or so through the whole system. So very clearly, there is some reason, some physical underlying reason why the solar system organizes itself in this way. And we speculate, we haven't proved it yet, and Christopher wants me to have a good think about this, and he's quite right. We need to think about, well, what are the underlying forces that push the orbits of the solar system into this configuration that they would relate with this simple number series like this. And we think it's to do with the conservation of energy. And we think it's to do with orbital resonance. And it's to do with nature doing things in an efficient way, which she always seems to. The path of least resistance, maybe. So for instance, we find with Jupiter, Earth and Venus, we can construct a very simple planetary index of when these planets are in line with each other, and the black line represents the planetary index, the red line is the sunspot series, and you can see that there is a close relationship. Even the shapes match between the planetary index in some cases and the solar activity variation. And this relationship stays pretty close. It gets a little bit out of kilter when you get close to one of these big solar slowdowns. It happened at the start of the 1800s, it's happening again now. So there's obviously some kind of relationship. I found that this relationship improved and got stronger when instead of looking at it as straight lines, you actually looked at the alignment of the planets along the Parker spiral, which is the spiral generated by the electromagnetic radiation of the sun and the variation in it. And this suggests to me that the big outer planets are affecting the sun through an effect on angular momentum and the transfer from spin to orbit, transfer of energy from spin to orbit. And the inner planets are maybe affecting the sun through electromagnetism. NASA has published articles on how the solar wind connects, as you heard from Piers yesterday, how the solar wind connects with the Earth's magnetosphere and energy comes into the Earth's atmosphere, particularly on the odd-numbered solar cycles, as Piers said yesterday. So pulling all these things together, I'm glad I put these articles on my blog without worrying about getting proper approval and publication in the scientific literature, because it moves things along faster. Somebody I've never heard of before popped up in the comments on my website and said, really interested in all this stuff you're doing. I've made a simple model and it's worked out quite well. I couldn't believe my eyes. Look at this. This is 4,000 years of the beryllium-10 record. The beryllium-10 is used as a proxy for solar activity. So in blue, we have the beryllium-10 record of the last 4,000 years. And in yellow, the yellow line is Rick Salvador's planetary model using 4 orbits. Jupiter, Earth, Venus, and Uranus, and some periods which relate to those periods in harmonic resonance with those periods, acting as modulators. Now, some people say, oh, you must have overfit this curve, there's got to be some kind of problem here. That's fine, they can say that. I look forward to them coming back with a better model that is as simple as this one.
Have you submitted it?
And the other noticeable thing here is what the history of the 10 beryllium shows us is when it takes a big dive downwards, you get cold periods like the Dark Ages and like the Little Ice Age. And conversely, when you're up at the top of the curve here, you get the medieval warm period. You get the Roman warm period and the modern warm period. And what this shows is that the sun was getting stronger all the way from 1700 at the end of the morning minimum, getting stronger all the way to 2003. So, although the IPCC offers a correlation between CO2 and temperature between 1950 and 2010, we're offering a strong correlation between solar activity and Earth's surface temperature over 4,000 years. And not only that, we have a model which can describe it accurately, which is more than they've got for their CO2 conjecture. So that's why I'm proposing this as a better theory of climate. Here's what that model projects for the next 85 years, up to 2100. It predicts very low solar activity, centering around 2035, as Piers said yesterday. And for the rest of the century, well, a bit of a recovery, but still...
Where's the 2035 on it? Can you show us that? Or is it the middle of the hump?
So 2035 is there.
That one. Right.
There. So we're not sure whether this will be a very long cycle or 2 very short cycles, or whether it will even really be possible to tell, because we might see very few sunspots during either of them, as in the Maunder minimum in the 1600s. And even after the recovery, we look like we're only going to get up to a peak of around 50 sunspots per month, and that's not enough to warm the oceans. The oceans will be discharging energy pretty much throughout this period, whereas during the 20th century, solar was high and the oceans gained energy. But the thing about the way that the oceans gain energy is you wouldn't expect to see much of a signal on an 11-year basis. We're talking multi-decadal stuff here, because the oceans have a huge heat capacity, and so they integrate the solar input into them in many ways. And so in order to understand the relationship between the solar cycles and Earth's surface temperature, you have to take a bigger view on things. You have to widen the context due to the thermal inertia of the oceans. We confirmed our model by using a completely different technique. What we did here, my good friend Tim Shannon, who's a very clever signals processing guy, he said, oh, years ago I wrote some software which will take a complex sound envelope and break it down into the underlying sine waves. So I thought about that overnight. I rang him back the next day. I said, so what happens if we give it the data from Judith Lean's solar reconstruction? He said, I don't know, let's give it a try. Well, what it did was it was able to find 7 sine waves, which when you added them together, reproduced Lean's Lean 2000 curve to an R squared of 0.99. Amazing. And what we found was that the length of the wavelengths of these sine waves were pretty close to these planetary periodicities that we'd been looking at. Now, Tim was very cautious and he was only prepared to give a forecast out to 2050. He wouldn't go as far as 2100 and doesn't want me to show what the model does after 2050 because he doesn't think it's really reliable beyond that. Fair enough, because we are, after all, using somebody's reconstruction of total solar irradiance here, not the actual sunspot record. But what it shows is a pretty strong decline in solar activity to the middle of this century. And so this is in agreement with the Salvador model that I just showed you, and quite a few other models that have been put forward by scientists such as the Russian Abdus-Samatov, and others. And so quite a few of us are coming to a similar conclusion from different directions using different methods of modelling. So we think that we're onto something and that we can now, with some confidence, predict solar activity. Just as a side note, Judith Lean was sent away by the IPCC 3 times to squash this curve flatter and flatter and flatter until the sun appeared to not vary hardly at all, apart from on its 11-year cycle. But if we look here, going back to the 10 beryllium that I talked about, that's used as a proxy for solar activity, 10 beryllium in yellow from 1650, and in red, the Central England temperature record. Now, it isn't a perfect match by any means, but it seems to me there's something there worth investigating. So, how did the IPCC end up thinking that the sun causes almost no effect on climate change? Well, here's part of the answer. One of the papers they rely on are by 2 people who are not solar experts. One of them is Gavin Schmidt, whose job it is to fudge the surface temperature records for NASA GISS. And the other is a guy called Rasmus Benestad, who I think works with the Potsdam warming central propaganda outlet for climate change.
No, he's Norwegian.
He's
Norwegian.
He's Norwegian, but does he not work at the Potsdam Institute?
No, he works at the Institute of Meteorology.
Okay, I stand corrected. Thank you. But what they did here was they took the solar record and they then subjected it to a kind of wavelet analysis using an off-the-shelf wavelet analysis program, but they forgot to untick the little box which ties the end of the series back to the same level as the start of the series. So you've got solar. So you've got solar, which increased in a secular way right throughout the 20th century, being forced to fit a curve which gets dragged back down to the same level as its starting point at the end. And so when we put them side by side like this, it showed very graphically the disconnect in what they were trying to do. The effect of that was that in figure 6, they show that the TSI, the total solar irradiance, goes up while approaching 2000. But according to the same guys in their next figure in the paper, the solar signature on the temperature goes down approaching 2000. This is complete illogical nonsense. And yet, the IPCC, which relies on very few papers for its assessment of the solar effect on climate, relies on this paper, even 4 years after Nicholas Gavetta published a paper showing them where they'd gone wrong. this is the effect of solar and temperature. They do co-vary, but Piers said yesterday he thinks that the 11-year cycle doesn't have much effect on the temperature record. One of the reasons it doesn't appear to is because the big El Niños tend to occur near solar minimum. So you get a big warming up of the ocean at solar minimum, and that kind of diminishes the apparent effect of the sun on the surface temperature record, because the sun has been creating all that hot water beneath the surface, hidden from the surface record in the Pacific warm pool for several years. And then when the sun stops pushing energy into the ocean so much, the ocean throws a load of energy out. It has the opportunity to release energy that's built up during the solar cycle. So this is the reason why there isn't a big, we're only talking sort of 0.1 centigrade apparent relationship between the 11-year solar cycle and the temperature record. But that is a bit of an illusion due to the fact that you've got this anti-correlation of release of energy near solar minimum, which is the big El Nino events occurring as they did in 2010, 1998, and going back through the 20th century. You can see this. The biggest El Ninos occur always near solar minimum. So that's why you can't see in the record a big correlation, a big, strong, powerful correlation between the sun and the surface temperature record. But nonetheless, the relationship's there because the sun is busy building up all that energy that gets released at solar minimum in the Pacific warm pool that's beneath the surface. Now, I'm coming towards the end, so questions in a minute is. What you have to do to really see the effect of the sun is integrate the data, as I said earlier, because the ocean has so much thermal inertia. You have to calculate. This is the solar curve here in this model. You have to calculate it by getting a cumulative running total, which departs from the figure at which the oceans neither lose nor gain energy when the TSI is at a certain average level. And that figure turns out to be about 40 sunspots a month, empirically found, which also happens to be the average sunspot number over the entire period of the sunspot record. So this is, when you make that cumulative total, what you find is that solar didn't have much effect through until about 1930 here, and then it starts to climb because the sun had some high cycles in the middle and the end of the 20th century. And then as we get to present day, the sun's just starting to weaken here, and we expect to see it falling off. So regard this line not just as a solar line, but as a, if you like, a proxy for ocean heat content.
But if that's a cumulative total, why does it start going down?
Because if you've taken as your start point the figure of 40 sunspots a month, then if you get a value that's below that, then it reduces the total, the cumulative total, instead of increasing it.
I see.
Right? So it acts as a proxy for ocean heat content in this way, I think. If you combine that solar curve with, in green here we have the Atlantic multi-decadal oscillation with a presumption it'll behave over the next 50 years a bit like it did at the start of the last century, and the Southern Oscillation Index in blue, and a line for CO2 as well, just to keep them happy on the other side of the debate. You see that all the magnitudes are quite similar. You've got the sun contributing about 0.25, CO2 contributing about 0.2, the Atlantic multi-decadal oscillation contributing plus or minus 0.15, and when you add all of those four together, this is the output from the model in blue. And as you can see, it matches the Hadley SST version 3 pretty well, until you get back to the early part of the 1900s where the data isn't quite so reliable. But I'm getting a 0.9, an R-squared 0.9 correlation there for monthly data. So there's not too many degrees of freedom either. So, I'm sure, I'm not a statistical expert. I'm sure that there will be experts who can pick holes in what I've done here. But I think that, from an engineer's perspective, This is a reasonable assessment of what's going on. We've had a strong sun, we've had CO2 going up, we've had the positive phase of the Atlantic multi-decadal oscillation, all from 1976 to 2003. No wonder the temperature went up. Question is, what was causing it? So if all those three variables went up, and now the AMO, the Atlantic's going down, the solar's going down, CO2 carries on going up, the temperature's leveled out, place bets now. What's going to happen next? Well, I'll tell you what isn't going to happen next, and that is, it's not going to happen like the IPCC say it is. What we've got here is, this is the mid-troposphere. This is where the mid-tropospheric tropical hotspot is supposed to be being generated in the atmosphere, which toasts us all from above by bathing us in long-wave radiation. And what those models predict the effect on temperature will be, well, we should already be up here, according to the IPCC. But in the real world measurements of the mid-troposphere from balloon data sets here in green, and the satellite data sets in blue, these are the real world measurements that we believe we can rely on more, and it shows a huge discrepancy. And I put it to you for your consideration today that the reason why there's this huge discrepancy is the IPCC has given much too strong a forcing power to CO2, only pulled down by the occasional volcano, to which they've also given too much of a negative power to try and pull the thing back into line here. But once there are no volcanoes, whoa, soar away. Here's what the real world says. And that's also what the solar data says. So I think I'll draw it to a close there for questions, and thank you very much for your attention.